This question set 2A in preparation for our quiz tomorrow. Question number 1 says the physical quantity. Do you guys know what a quantity is? Like it's a variable, the physical variable, the quantity that has the same unit as impulse would be. What would it be? Yeah, it's going to be momentum, because we define impulse as what? Change in momentum. So it's going to, of course, have the same units as impulse. The answer would be D. Force, work, and power, really physics 20 things, right? Okay, but in the end, certain things in physics 20 that we do have to know in physics 30, but generally they're more like straightforward things like force, work, and power, as opposed to like, you're not going to get a projectile motion question type thing, for instance, in physics 30. It tends to be more basic things than specific things, basically things like this. All right, let's take a look at the next question here. This scenario bothered some people. I know there was a number of people that asked me questions on this scenario and the questions that went along with it. It says, airbags are designed to deploy when a car moving at a minimum speed of 18 kilometers per hour comes to a crashing stop. How come I circled that? Yeah. Yeah, if I want to do a calculation with this, and I still don't know what I'm going to do with this yet, but if I do have to do a calculation with it, I want to be in meters per second. It comes to a crashing stop. The impact sensor, also moving at 18 kilometers per hour, consists of a small steel ball, which is held in position by a magnet. On impact, the ball breaks free in 1.00 times 10 to the negative 3 seconds and slides within a cylinder. The ball makes contact with 2 electrodes at the end, activating the airbag. So that's what happens. This ball rolls down here and ends up completing this circuit. The electricity flows through here, flows through the metal ball, and then flows through here. And then it actually, with the electricity, creates a chemical reaction in this powder that's somewhere in there, which creates a gas, not air, but some gas, really, really quickly, and inflates this airbag in a ridiculously short amount of time here. What's the magnitude of the force required to break away from the magnet? Sorry? The answer is C, you're right. But how do we get that? Well, remember the last week we talked about when we see a time and a force. We see a time and a force in the same problem. What do we think when we see force and time in the same problem? Like what should come to our mind? Yeah? Yeah, F and delta T, and F and delta T is impulse. So that's what we want to think here. Delta P is equal to F times delta T. Now that's also equal to M times delta V, right? We're going to use 2 of the 3 parts. There's 3 parts here, 1, 2, and 3. We need to use 2 of the 3 parts. Since we're looking for force, it's pretty clear, I think, that part we're going to use, right? F times delta T. And we also have the time. So like it's pretty clear that we're going to use that. Now, what's the other part? Okay, we're using part 2, or we're going to use part 1, or we're going to use part 3 along with that. Part 3, yeah, we got the mass, and we can find the change in velocity by saying VF minus VI, right? So we're going to say F is equal to M times delta V over delta T. The mass of the steel ball is 0.05 kilograms. Delta V would be, well, what are we going to say, 0 minus 5 meters per second. Where did the 5 come from? Yeah, 18 kilometers per hour. The time interval here is 1 times 10 to the negative 3 seconds. We do the math there. Whoops, negative 3. I do the math there. It works out to be C, 2.5 times 10 to the 2 newtons. Does that make sense? 250 newtons. Now, this is one of the 2 that tended to bother people, I know. This one says, if the car was moving at 18 kilometers per hour, the maximum speed of the ball immediately after impact would be what? Well, listen, the car is moving at 18 kilometers per hour, right? How fast is the ball moving? 18 kilometers per hour, 5 meters per second, right? If you slam on the brakes, the car stops. Does the ball stop? Maybe. If the ball stops, and afterwards the ball is moving at 0. But if the ball is released, what's the maximum speed that the ball can be moving after it's released? 5 meters per second. How come 5? 18 kilometers per hour, that's how fast it was moving, right? The most it can be moving is the speed that it was moving before it was released. So the answer for this one would be C, 5 meters per second. Make sense? Object in motion stays in motion at a constant speed until acted upon by an unbalanced force. This ball is moving at 5 meters per second. It'll keep moving at 5 meters per second unless it's acted upon by an unbalanced force. Now the magnet could cause it to stop. The magnet could cause it to slow down, but the most that it could be going, okay, would be the 5 meters per second that it was moving. Nothing's going to cause it to speed up. And 4, if the car was initially moving at 18 kilometers per hour, the driver had a mass of 70 kilograms and the airbag stopped him in 0.10 seconds, the magnitude of the average force acting on the driver would be what? Again, we've got, in this question, we've got a time and we've got force, so this is going to be impulse. I'm going to use F times delta T is equal to M times delta V. Almost the same as that other question. Now, how many of you guys did this? Set those two equal to each other. Okay, how many of you guys said delta P is equal to M times delta V, got a number for it, and then said delta P is equal to F times delta T? How many of you guys did that? Okay, which way is better? Yeah, neither way is better, right? This is one less step, but there's a little bit more to the step. So 6 to 1, half dozen to the other here. My mass is 70 kilograms. Delta V would be, the man stopped in 0.1 seconds, so his final velocity would be 0. His initial velocity would be 5.0 meters per second, and the time interval here is 0.10 seconds. The force here, when we do that calculation, works out to be 3.5 times 10 to the 3 newtons. And number 5, the entire process from impact to airbag inflation takes less than 3 times 10 to the negative 3 seconds. During this same time, how far forward would the passenger move? So the passenger is not wearing a seatbelt. You guys know why you wear a seatbelt, right? It's so directly a Newton's first law thing. You are in motion at 110 kilometers per hour on the highway. If you come to a crashing stop, we hope you don't, but if you do, and you're not wearing a seatbelt, you will continue moving at 110 kilometers per hour until some unbalanced force stops you, which would be the windshield / the road. Okay, and that tends to hurt. Sometimes it doesn't hurt because it's so quick. In the end, if you're not wearing a seatbelt, you're going to continue moving at the same speed you were moving. How fast was this person moving? 18 kilometers per hour. How fast is this person moving after the car stops if the person isn't wearing a seatbelt? 18 kilometers per hour. How far do they go in this amount of time if they're moving at 18 kilometers per hour? Do not make this question harder than it has to be. We're doing this stuff in Physics 20 right now. V is equal to delta D over delta T. This is a Physics 20 question. What's the speed of the person? 5.0 meters per second. What's the time? 3.0 times 10 to the negative 3 seconds. We multiply those together, we get 1.5 times 10 to the negative 2 meters. That's it. That's it. Now, seatbelt, okay, locks in place, and you don't end up going that far. Guess seatbelts hurt. You ever been in a? How many people have ever been in a car crash here? I don't know if I've asked you this question. Yeah? Seatbelt hurt? Yeah. Sometimes seatbelts actually break ribs and actually do significant damage to people. But you got to figure if the seatbelt applied that much force on you to break your ribs, you hate to think of what the alternative would have been, right? If the good thing broke your ribs, then the bad force would have broke a lot more than your ribs, right? Make sense? Yeah. Now let's have a look at practice question set 2B, which is the second half of this practice that we have for our quiz tomorrow. We have some information in a box here. Know that when we see this, and we will, your diploma exam is probably going to be something like 36 pages-ish for a 50-question test. We're going to see some reading. And sometimes that reading is a lot longer than this. Sometimes it's an entire page or longer. I once saw an entire page of information. It said at the top of it, use the following information to answer the next 14 questions. And then along with that, down the road, there was use the following additional information to answer the next 3 questions. And that happened 3 or 4 times, the following additional information. Those 14 questions took something like 10 or 11 pages. So 10 or 11 pages was based on one scenario. But the good news is, when you see a box of information like this, even if it's a lot longer, the vast majority of it is not relevant. Most of it just doesn't matter. We just have to look at what does matter. In this question, it says the starting gate of a downhill ski race, the skier pushes with his arms and legs to get as fast a start as possible. The skier leaves the starting gate with an initial speed of 1.6 meters per second. And then it goes on to talk about the race course, steep and flat sections, 80-meter finish line, speed of 20 meters per second. At the end of the steepest section, 33 meters per second. The mass of the skier is 68.2 kilograms. We want to find the magnitude of the impulse as he leaves the starting gate. As he leaves the starting gate. Listen, the strategy that we want to follow when we see information like this is to skim it. Usually we see, or at least sometimes we see, a lot more information than just this. We really want to follow this strategy when it's, a page of information. But even this, skim it. Just skim it. And then read the question. And then go back to the information now that you know what the question is. And that makes it a little bit easier to see what you're looking for. Your English teachers probably tell you something similar to that when you're doing reading comp. They tell you to read the question and then go back and look at the information. Yes? It's not that different, right? It really isn't that different. So we read this, the magnitude of the impulse as it leaves the starting gate. We realize, look, this is all that really matters. This is where the person is leaving the starting gate. This is the person going down the hill. So what? How fast is he moving when he reaches the end of the steepest section? It's irrelevant. Don't make this harder than it has to be. We're looking for the impulse. Impulse we know is equal to F times delta T, and it's equal to M times delta V. You're going to use two of these parts, two of the three parts. Which two parts do you want to use? Well, one of them is really easy, right? This part, right? Looking for impulse, got to use this. M and delta V, yeah. Careful, not M and V, M and delta V, right. Looking for the impulse. We do need the mass from down here, I guess, 68.2 kilograms. What's delta V? Well, VF minus VI. How fast is this person moving when he leaves the starting gate? Yep. 1.6, not 33.3 or 20 meters per second, right? This has nothing to do with the starting gate. Let's just look at what's relevant here. We leave the starting gate at 1.6 meters per second. How fast is the person moving before they leave the starting gate? Yeah, presumably 0, right? Standing in the starting gate. So it's 68.2 times 1.6. When I do that, that gives me an answer of A, 1.09 times 10 to the 2 Newton seconds. How many people got that? Okay, good. How many people got kind of sidetracked by these other numbers down here? 20 and the 33.2, 3? That's okay if you did. But just take a step back from this and look at why those don't matter. Don't just use numbers because they're there. Don't just use numbers because they're there. Use numbers because they're relevant. We're looking for the person leaving the starting gate. We don't know or care really what happens to them down the hill. Okay, let's take a look at number 2, which involves the information that we see down here for this recurve ball. 130 newtons, full drop 70 centimeters. Here's the mass. What are we looking for here? Oh, we're looking for the magnitude of the impulse. Looking for the magnitude of the impulse here. That's a tricky question. Tricky question. Why? Well, because I know what F is. I don't know what T is. I know what M is. I don't know what delta V is. I can use, to find impulse, this, right? I can use this, or I can use this, but I'm missing something from both of those equations. How many people think they got an answer for this? Yeah? What did you do? F times T or M times delta V? Okay. Oh, okay. So you used M times delta V, and then you used force to find acceleration. So A is equal to F over M, right? By the way, guys, you try something like this, We don't know necessarily if this is going to lead us to an answer. Is there any risk in doing something like this? Absolutely not. Is that a valid equation? Yes. Then there's zero risk to it, right? Worst case scenario is it doesn't get you what you're looking for. That's the worst case, and you try something else, right? What is the force? 130 newtons divided by the mass, which is 20.6 grams, or 0.0206 kilograms. We divided that by 1,000. Now, I didn't do it that way, so I don't have the acceleration. What'd you get? 6,310.67 meters per second squared. That's high, but we're talking about the acceleration of an arrow as it leaves. It's going to be moving pretty fast in a very short period of time, so the acceleration will be high. That doesn't seem completely unreasonable to me, even though it's really, really high. Then what? Okay, so VF, yeah, that one that we seem to use so often, right? So VF is equal to, this would be 0, right? 2 times 6310.67 over an acceleration distance of 0.70. And that gives us VF. I think, now I did it differently, but I think you're going to get lightning fast calculation in my head here, 93.9944. Wow, isn't that quick? I didn't do it that way. I did it a different way. But this equation is valid. This equation is valid. That means it's got to produce the same answer as I already had, right? Just that I got a different way. And then, now it's easy, right? We're just going to say delta P is equal to M, which is 0.0206 times delta V, 93.9944 minus 0, right? And when we do that, I think we get, I got a little scribble out here, but I think it was 1.94. Is that right? 1.94 newton seconds. Good. How many people did it this way? More or less. Okay. Anybody else get 1.94? It's a tricky one, eh? It's a hard one. You know what I did? By the way, what physics principle did we use right here? What physics principle did you use? If you go look at the list of principles on the back wall or in the bottom left-hand corner of your data sheet. Yeah, that would be principle number 1, accelerated motion if you were asked, right? Now, I didn't use accelerated motion. I didn't use principle number 1. I did this. I said work, remember this from Physics 20? Work is equal to delta E is equal to F times D, right? Delta E is 1/2 mv squared minus 0 equals F times D. I know what F is. I know what D is. I know what M is. I solve for VF there. And when I solve for VF there, I got 93.9944 meters per second. And then I subbed it into M times delta V like you did. Good? What physics principle did I use? Yeah, you used principle 1. I used, principle 1. I used principle what? Principle 3, good. That's called the work energy theorem. Work is equal to the change in energy. So both of those are correct. If you were asked which physics principle you used, 1 or 3 would get you a correct answer for that. Good? Anybody do it my way? That's too bad. I like my way. But your way is just as good. In fact, if you combine these two equations, did some rearranging, you'd end up making it look exactly the same, even though you're thinking of it in two different ways. Good? Okay, let's finish off with a nice easy one here now. I think a nice easy one. Rock climber falls and is saved from injuries by a climbing rope that is slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse, because the elasticity results in what? Hey, what's happening? Like, what is it that in the absence of elasticity, what is it that's going to hurt this climber? When this climber falls, it's not the fall that hurts the climber, it's the force. It's what force? It's not the fall that hurts the climber. Falls don't hurt anybody. It's the, Jackson? you add the tension of the rope, I'm thinking of, it's the stop. It's the abrupt stop, right? When you're falling, you're fine. If you can put out of your mind the fact that you're going to die, then the fall would actually be quite fun. It's just the whole idea of, in the back of your mind, knowing this is not going to end well, that you would have a hard time getting past. The fall's fine, though. Maybe not psychologically, but physically the fall's fine. It's the sudden stop at the end of the fall that makes you not physically fine. So if we can think of that as an object stopping, you, the climber, are stopping at the end of this rope, then we would know that the impulse experienced by the climber is going to be no matter how the climber stops, whether it's a rope that's elastic or not, the impulse is going to be the same. So what do we want to do? Increase the time, which decreases the force. Which one's the answer? Decreased force during an increased time interval. The answer would be A. Remember I told you, like, probably 90% of exams, we get this question? Sometimes it's an airbag. Sometimes it's a climbing rope. Whatever it is. If it cushions an impact, if it cushions a blow, it's same impulse, increased time, decreased force. Got it?